Hello, Butcher. So now let's all start class. So what they has given us, this is numerical, and this is a temperature and distance of the hot end. So this is the rod, and in this there's a rod. In that rod is a graph of temperature and end of the distance. The hot. Suppose something like this is some rod, right? And this is at T high temperature, and at any this distance is x. So they has given graph of T and X in this T and X graph is. Now they're asking us, these are four options you need to specify. The temperature gradient is constant. The values has uniform cross section area. So this road has a uniform cross section area. Cross section is increasing or cross section is decreasing. This is all about this. So Bacho, you just try to solve the question, pause it for a few minutes and then solve this question. Bacho, if you see temperature and distance of the hot and this x, we have drawn this graph, right? So this graph, you write this graph, slope of this graph is dt by dx. So slope of this graph is represent nothing but the temperature gradient. Okay. So if you see slope, if you see modulus of the slope, that is increasing. Modulus of the slope, modulus of slope is nothing but increase. Slope is this graph is giving us temperature gradient. Slope modulus of this graph is a modulus of temperature gradient. As you see, bacho, modulus of the slope is increasing, right? Modulus of slope is just inclination, right? And that inclination is increasing. This side this and this here. So temperature gradient is increasing, modulus is increasing. This is temperature gradient. As you know, throughout the rod, whatever be the rod, whether this kind of rod, or whether this kind of rod, right? Or whether this uniform cross section area rod, H is always constant throughout the section. H is always constant, and for this rod K is also constant. They has given us. So this and this part is constant. So you can say dt by dx is inversely proportional to A. So you can write dt by dx is inversely proportional to A. So now, bacho, if dt by dx is increasing, now A need to decrease. Area, so area along the direction of current flow is decreasing because dt by dx slope of the rod is increasing, right? So I think this is the answer, which T high and this is T low. Okay. This is the next problem. These are two roads are given and these roads are in the series. So what they have given is this end temperature is 100 degree, this end temperature is 0 degree. They have given us thermal conductivity of this rod is 2K and area of cross section is A. Thermal conductivity of this rod is K and area of cross section is A. So area of cross section of both rods are same. Okay. Thermal conductivity first rod has double than the second, and it has length 2L by 3. Its length is L by, the total length is L. So they're asking us find out the temperature gradient. You need to find out temperature gradient of both the rods. Okay. Pause the video for a few minutes and solve this first. So, bacha, as you know, to find out temperature gradient, if here the current flow in this part is same as current flow in this part. Okay. So both the roads will have the same current flow. So if you want to write current flow in the first road, you can write H equals to P minus, suppose this junction temperature is T. T minus 100 divided by R1. And same current flow is here. Actually, you write it like 100 minus T limit, right? Write like this here, 100 minus T by R1. Similarly, here you can write this T minus 0 by R2. So in this, both has the same current, right? Both has the same heat current. So temperature gradient in both rod cannot be same, because when you write the formula of heat current, it says minus Ka dt by dx, right? If both the rods have same H and A is also same, both have same H, same A, K are different. So both rod K are different. So dt by dx, which is temperature gradient, has to be different for first rod and the for second rod. But throughout the first rod, temperature gradient will be uniform, and throughout the second rod, temperature gradient will be uniform. Because throughout the first rod, area is same, area is not changing, and throughout the second rod, area is not changing. But temperature gradient in both the rod will be different. Okay, by simple this condition. So now your task is just to find out this temperature, and it's very simple. You find out this junction temperature, and you can find out the temperature gradient. If you remember formula for junction temperature, see, I told you in the last class. So junction temperature T equals to this 100, this side temperature, okay? So this side temperature, so this side temperature 100 into this side resistance. So 100 into R2. Suppose this side resistance is R2 plus 0, this side temperature, into multiply by this side resistance, R1 divided by R1 plus R2. And you know how to find out R. R क्या होता है बच्चों? R होता है L by Ka. If you remember for a rod, this is R. R is nothing but L by K. So for first rod, R1 equals to its length. Its length is 2L by 3 by K. K is 2K by K. This is R1, right? Similarly for R2 also you can write this length of this L by 3 by K and K. So R1 and R2 तुम find out करो. Find out R1 and R2. Put this value here. So I have done this numerical. I got this value 50 degree. Okay, but you can solve also. It's very simple numerical. It's not a difficult one. Substitute this all the values, right? Now, second part of the numerical, what he asked, he says as draw T versus X graph. So T, temperature of the rod versus this X graph. If this is the X axis, so along this side it is hot end and this side it is cooler end. So we are moving from hot end to cooler end. Now we want to draw the graph, T versus X graph. So now, but as you know, T versus X graph, slope of this graph represent the temperature gradient, because dt by dx is the slope of this graph, which represent temperature gradient. Okay. So as you have seen this part, bacho, temperature gradient, you can write this H equals to minus Ka dt by dx. So in both the roads, H are same, A is same. In the both the roads, if H and K are is same, so K dt by dx, which is temperature gradient, you can write H by Ka. So H and A both are same, so temperature gradient is inversely proportional to K. So if K is higher, temperature gradient should be lower. Temperature gradient with the slope. Okay. So if you see in the first one, in the first rod, temperature K is 2K. This is 2K and this is actually K. So this will have less slope, inclination, less inclination, and this second one has the higher inclination. Okay. Now next, what we need to do, heat conduction in 3 dimensions. Till now we have seen heat conduction in 1 dimension. So till now in all the questions, this was the rod, and this side temperature is T high and this side temperature is T low. So heat was flowing like this. So this was a heat flow in 1 dimension. Now this is the heat current in 3 dimensions. So what is the numerical this time? So we have this cylinder. In this cylinder, So this is the heat cylinder. This is a cylinder, and cylinder specification is inner radius of the cylinder is R1, outer radius of the cylinder is R2, length of the cylinder is L, and between these R1 and R2 we have filled a material, right? This is a filled material between the two cylinder R1 and R2. Only this part is filled, only this part is filled, and the thermal conductivity of this material is K, and K is also constant. Inner temperature is T high, outer temperature is T low. This is a specification of the cylinder. From this corner, we have covered by cylinder from insulating material. This side is also covered, cylinder is covered by insulating material. So now heat cannot flow towards this side, right? Toward this side, there is no flow of heat. So inner temperature is high, outer temperature is low. Heat will flow radially outward like this in all the directions, right? So if you imagine it three-dimensionally, the heat will flow in all the direction like this. Now in this, we need to find out the formula for heat current. If you see, Bachu, from the top view of the cylinder looks like this. The heat will flow in all the direction like this. Okay. Now for heat current, you have two formulas. Okay, so now for heat current, you have two formula. One formula is this, but you remember when to apply this formula? You apply this formula when throughout the length, area remain constant throughout the length, and length you need to take in the direction of heat current. In the direction of heat current, you need to take the length, and throughout the length, the area should be constant. But if you see here, Bacho, this is the direction of heat current, right? If you are taking this is the direction of heat current, this is the length. Length of heat flow is from R2, from R1 to R2. This is the length from this point to this point, the heat flow. But if you see area of cross section, it is changing, right? If you are near the R1 surface, area of cross section is less. As you are going towards the outer surface, area of cross section increases, right? If I draw this cylinder, see if I slow the cylinder here, any cylinder here, suppose you slow this cylinder here, right? Then the current is flowing by this area, right? By this area. Current is flowing by this area, okay? By this area, current is crossing this area. So A is the area in the formula. A is the area perpendicular to the flow of the current. Okay. So this area, this is crossed by the current. If you see this area continuously increases when you move from R1 to R. So we need to use a differential formula for this. So we'll use this formula. We need to use differential formula. So how to? We will say this is small part which has a length dr, and radius of this is r, and this part has a length L. Okay, this part has a length. This is a cylinder. This is a cylinder. Okay, this is a cylinder. So, but I have some downside. We are looking only at the top. So it looks like this. Right? It looks like this. If you see it complete in three dimension, it goes a length is there. Okay. Now this is in this small thickness dr, we can write down the formula of current H equals to minus K dt by dx. Now, but as you know, there is no heat accumulation anywhere. So whatever the heat current in this part, heat current in any part should be the same. Heat current between this part and this part, the same heat current should be from here to here. And same heat current should cross any cross-sectional area, because you know there is no accumulation of heat. So there is no temperature is not changing. We are in the steady state. So throughout the cross section area or throughout the length, the same heat will flow. So in this formula, H become constant. So here this H become constant. Now let's cross multiply it and it's differential integrate. So H and dr will come this side. H into dr equals to minus Ka into dt. Now A is the area. A is the area perpendicular to which current is flowing. So now this area, I have taken this part, this cylinder. This radius is R and its length is L. So by this cylinder, current is crossing, right? By this cylinder, current is. The area of this part is 2 pi RL. So I've written it's 2 pi RL. This is the area, 2 pi RL into dt. Now we have just integrated this. Now what is H into dr? I have taken this R here, okay, and the remaining part are here. So 2 pi KL is constant dr. Now this R goes from R1. When it is R1, temperature is T high. When it is R2, temperature is T low. Then we have just done the integration of this. We've done the integration H into integration of this L and R equals 2 pi KL T low. This is T low minus T high. I've arranged this. This is the formula which you need to remember. Okay, this is the formula when K is constant for the cylinder. Okay, the formula is 2 pi KL T low minus T high divided by ln R2 minus ln R2 by R. So if you don't want to write here minus, you can put it T high minus T low. One problem based on cylinder. So this is a cylinder. Okay. So concentric cylinder, the inner temperature is T. You can write this is T high and you can write it T low. Okay. This is T high, T low. And you have filled the material here, which has a thermal conductivity K. So current is flowing like this. Okay. Inner radius is R1, outer radius is R2. Now what he's asking, find out the distance from the axis where temperature is half. Where temperature is half, okay, become half. Half meaning, suppose this is 100 and this is 0. So find out this distance where temperature is 50. That he is saying. Okay. Okay, bacha. So now solve this problem. Pause the video and solve this problem. Find the value of R in terms of R1 and R2. If possible, T1 and T2, या T low or T high is required, you just solve this problem. So, bacha, if you see a formula for heat current in case of cylinder, this is the formula. H equals to minus 2 pi KL, T2 minus T1, this is T low minus T high divided by ln2 by R, ln R2 by R. So R2 is the outer radius, R1 is the inner radius. Okay, and that is the formula. So suppose at some distance R, suppose now temperature is half. So half meaning how we will write this half is T1 plus T2 by 2. This is half of this. Okay. So suppose this side temperature, one side is 100, other side is 20. So half का meaning यहाँ पे क्या कह रहा हूँ बच्चों मैं 100 plus 20 by 2. It becomes like 120. It becomes 60. That is the meaning of my half here. Okay. So bachcho, now if I want to write the heat current in this part only, from R1 to R, in this part only, formula the heat current is H equals to minus 2 pi K is constant throughout it. L is the same. You will write here, suppose temperature is T. So T minus, I'm calling it T1, okay? I'm calling this T1 because minus is T minus T1 divide by, I will write this ln, this temperature, this length is R by R1, okay? And now if I want to write the heat current between this part, the second part, heat current in this part from here to here, then again you can write that this is also like same cylinder. You write here minus 2 pi KL temperature. This side temperature is T2, okay? this side temperature is T2 minus T1. Okay, T1 नहीं बच्चों, T1 गलत लिखा है, this is T. Okay, so this tells this is now I'm writing about this point and this point. So now temperature is T2 low minus high, T2 minus T divided by Ln, R2 by R, right? To cancel out this part, and T can be written as T1 plus T2 by 2. You substitute the value of T here, this one. So this is T1 plus T2 by 2 minus T1 divided by Ln R by R1 equals to T2 minus T1 plus T2 by 2 divided by this Ln R2 by R. To simplify this, you will get the answer R equals to root of R1 into R. To simplify this, you get this answer. Let's see the next numerical. What is next numerical? Two thin concentric cell made of copper of radius R1 and R2. So where R2 is the outer radius is R2, inner radius is R1. R2 is have a material of thermal conductivity K field between them. So there is this material, this thermal conductivity K, and this material is field between them. Okay, this is field, completely field. Now in this we need to find out the formula for heat current. So bacho, this problem is also again the same problem. Heat this time is so the inner temperature is I'm calling it T high. Outer temperature is T low. Thermal conductivity is K. Radius, inner radius is R1. Outer radius is R2. So here also current will flow radially, right? This way it is current will flow like this. Almost if you see this theory is from the wavefront front, because in wave theory also the energy flow, right? And their energy flow here it is current flow. So if you call in terms of wavefront, here the wavefront will be spherical part. In the previous problem, wavefront was like the cylinder. Okay. This question is also like three-dimensional current flow. Okay, here also the area of cross section is continuously increasing. If I'm going from R1 to R2. Okay, so first the perpendicular area you need to write perpendicular area of the current flow. This is the area. Okay, this is the area. As you are moving outside, this area is continuously increasing. So we'll use a differential formula. H equals to minus K dt by dr. So as you know, but H is throughout the cylinder will remain throughout the sphere will remain the constant. It is a sphere. So throughout the sphere, H will remain constant. So from here, whatever current flow in any cross section, the same current will flow throughout the complete sphere. So H is constant. H into dr equals to, I can write this minus K into d. H into dr. So what I have taken? I have taken this small part. This is a small part. This I have taken is a sphere of thickness dr. So I have taken this sphere of thickness dr and radius r. I want to write down the current formula for this sphere. Across this sphere, the temperature difference is dt. So across this sphere, if you see, bachcho, ye hai kya? If I take this sphere outside, so this sphere, this is my radius, and this thickness is dr, and temperature difference across this sphere is dt. Okay, so now you can write down this formula. So this is the formula. H equals to minus k dt by dr for this part. This is sphere which has a thickness of dr and temperature difference across this is dt. Now H is constant throughout the complete sphere. You take H this way, you can write H into dr equals to k. Now area, it is a is the area of the cross section which is perpendicular to the heat current. So the area of that sphere become 4 pi r square into dt. Now simply what you need to do. Okay, so now you just need to H into dr equals to 4 pi k dt. R square will come this side, this r square will come this side. I will integrate when r equals to r1, temperature is T high, r2, temperature is T low. You will integrate it and answer with the answer. We will integrate all this, substitute all the value, but just solve all this, and this is the formula for heat current in the concentric sphere, where inner sphere inner radius is r1, outer radius is r2, and the material field between these two spheres has a thermal conductivity k, which is constant. So this formula is minus 4 pi k, T low minus T high, r1 r2 r2 minus. Okay, bachcho, so it's done. I have done almost, conduction is almost done. Little bit part is there. I will complete the conduction part in one more class, and radiation will be